Okay, here we are in StatCrunch. We're going to look at the applet for confidence intervals first. So we go to applets, confidence intervals for a mean. And let's say that our mean is 50 and our standard deviation is 10, and we're talking about a normal distribution. If we have 95% confidence and we have a 10 sample size, then when we run this 100 times, you can see that the red marks are the intervals that don't contain the actual population proportion. We don't know, like if we were estimating that it was 50, we wouldn't know if it was 50, but we do know because we're running an applet. But notice that we calculated 100 intervals and only twice did the interval not get captured by our sample data. So that's actually 98% when we were expecting 95. Let's reset it and do 100 again. There's one, there's two. Again, we're running with 98%. 1, 2, 3, 4, 5, 6 now. So this is 94%. So you can see what happens with the confidence interval. When you take your sample data and you calculate an interval, remember the sampling distribution for sample means, there's so many different ways that you can come up with samples of size 10. Well, when we do this, sometimes we're going to capture the true population value and sometimes we're not. So we're 95% confident that our interval is going to capture it. And sometimes we get lucky and it's more, and sometimes it's less. But the majority of the time, let's say I do it 1,000 times, 94.91% would have been our confidence interval, because right here in the prop contained in the top right, that tells you the number of times that the value was captured. Okay, going to stat, we're going to use z-stats for the problem we just did. And the reason is because we know our sample standard deviation, or our population standard deviation. They told us that it was 16. And again, this rarely happens. It happens like 99% of the time that we don't know it. So oftentimes we're going to be using t-stats, not z-stats, but that's on the next page. So we're going to do one sample with summary. It's always with summary. Our sample mean was 260. Our standard deviation was 16, our sample size was 114, and we wanted to do a confidence level of 98%, and then we compute. The lower limit, as I said, was 256.514, and the upper limit was 263.486. It calculates your standard error for you here, gives you your sample mean and your sample size. Now, I keep talking about how we don't know the standard deviation of the population. Let's focus on that. Okay, William Gossett and the search for better beer is our introduction to the t-distribution. William Gossett is a statistician who actually used to work for Guinness, and he is the person who is credited with finding what they called students distribution, and then they started calling it the t-distribution. What happened is they realized, or he realized, that the normal curve didn't really match sample sizes that were less than 30. And so he noticed that there was a different normal distribution for the sample sizes from 1 basically up to 30. And what you'll notice in a t-distribution is that you have fatter tails here. So you've got more weight here and they're a little bit skinnier down here. As the sample size increases, your tails shrink down and your distribution goes up and becomes more normal. So the dotted line here is what a normal curve truly is. And so as the degrees of freedom increases, you're just pulling that normal curve up, which causes your tails to get lower and your top to get higher. Now, in the distribution, there's some similarities. It's unimodal. There's that single peak. It's symmetric. It's centered at 0. But the larger the degrees of freedom, the closer the t-model is to the standard normal model, which is why we check that condition for n greater than or equal to 30. That's kind of our sweet spot of when we can really use normal calculations. The difference between the t-model is the t-model has more spread, fatter tails, and there has more probability in the tails, less in the center. The t-model is a good fit for the sampling distribution when sigma is unknown. Okay, if sigma is known, use the normal model instead of the t-model. So in StatCrunch and in general, if we know sigma, we do z-stats. If we don't know sigma, we use t-stats. And we have to focus on knowing the degrees of freedom. And the degrees of freedom, there's a whole lot of information about degrees of freedom. It's kind of a tricky subject to wrap your head around. So just trust me that the degrees of freedom for one sample is n-1. For two samples, you're going to let StatCrunch calculate it for you because it's actually very complex of a formula. Working on the learn by doing. According to the website collegedrinkingprevention.gov, about 25% of college students report academic consequences of their drinking, including missing classes, falling behind, doing poorly on exams or papers, and receiving lower grades overall. A statistics student is curious about drinking habits of students at his college, and he wants to estimate the mean number of alcoholic drinks consumed each week by students at his college. He plans to use a 90% confidence interval, and he surveys a sample of 71 students. The sample mean is 3.93, and the sample standard deviation is 3.78. So let me tell you the things that we have. We don't know mu. This is actually what we want to estimate. Since we don't know sigma, we must use t. We want 90% confidence. We know that x bar is 3.93. We know that the sample size is 71, which means we also know that the degrees of freedom is 70, n-1. And we also know the standard deviation of the sample is 3.78. And we have our confidence interval is x bar plus or minus the t critical value for 70 degrees of freedom times 3.7, or times, I'll keep it with symbols, times s over square root of n. Okay, well, we don't have a t-distribution chart that we're going to use. We need to go to StatCrunch to get this calculation. So let's do that. Okay, stat, t-stats, not z-stats, because we don't know the standard deviation. One sample with summary. We know that our sample mean is 3.93, our sample standard deviation is 3.78, and the sample size was 71. We're doing a confidence interval for 90% confidence, and we're calculating. This gives us a lower limit of 3.182 and an upper limit of 4.678. This tells us our standard deviation, our standard error, our degrees of freedom, and our sample mean. I'm not going to write it out, but if I was to interpret this in context, I would say we are 90% confident that the interval 3.182 to 4.678 captures mu, the true mean number of alcoholic drinks consumed each week by students at this college. Okay? Did I get this? Suppose the engineers in the previous example from OLI want to make a 99% confidence interval. They plan to use the same sample size of 45 cables. So right now we have n equals 45, which means our degrees of freedom would be 44. We also have 99% confidence. And they say, let's use the applet to find the critical t-value that they're going to use for computation. We're not going to do this. We're going to construct a 99% confidence interval based on the sample. So we have x bar, we have s, and we have n. And then they're asking what happens if we increase our confidence interval, what happens to the margin of error. Remember that our margin of error is when we are adding to and subtracting from the mean, or actually with sample data, it's how far we are going to capture. So if this was a 90% confidence interval, to get more confident, I go further out, which means my margin of error increases. Okay. Once again, let's head back to StatCrunch. Going into stat, t-stats with summary, we have a sample mean of 768.2. We have a sample standard deviation of 15.1. Our sample size is 45, and we are doing a confidence interval for 90%. This gives us an upper limit of 771.982 and a lower limit of 764.478. Here is a t-distribution chart with degrees of freedom on the left-hand side and whether we're dealing with area and one tail or two tails and what the critical value would be. This can get pretty complex, which is one of the reasons why we are just allowing StatCrunch to be our calculator for us.